We have the exam on Friday. So today's Monday. By the end of today, I'll let you know the cutoff point, okay? And then Wednesday, the second half or some portion of toward the end of the lecture, I will leave available for answering questions that you may have. So hopefully by Wednesday, you'll have studied enough where you know your strengths are and your weaknesses are. So come prepared on Wednesday to ask any questions that you need clarification on before you walk in on here on Friday to actually take the test, okay? So we've been covering transpiration and looking at the forces involved. So thinking about the plants around here, the C3 type plants around here, at night, are they doing transpiration? So if they're not doing transpiration, what must have happened to stop transpiration? What did they do? Yeah, they closed their stomata. Okay, they closed down their stomata. So if they do that, transpiration, which is the movement of water through the plant body, will have stopped. So what I'm trying to get at there is that the force generated for transpiration is in the leaf tissue. That's where it's generated. And we said that it is a negative pressure or a tension that the water column is under. Let me go back. So once the stomata open, by default, water vapor starts exiting the leaf. It just happens. As soon as that kicks into gear, you get that negative pressure or that tension developing on the water column. And so you can think of it like the water is getting sucked up the plant. It's like you put someone that has a straw, and it is sucking up. All right, so it's not being pushed up the plant. That's what they first thought, because they already knew about positive root pressure. But that only holds true under very certain special environmental conditions and with really short plants. Otherwise, it's the negative pressure, the tension forces generated in the leaf. So it's like it's sucked up. Literally, the water is getting sucked up because you get a tension gradient. You get really lovely, good negative pressure in the leaf and less negative pressure if you were to measure it down in the roots. And so you have a gradient, a pressure gradient or a tension gradient, to be more precise. It would be a tension gradient. Yeah. It's more the pressure difference. Pressure difference. Yes. 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 Yep, you're welcome. So it's this pressure difference. You have negative high, so that it's very negative pressure up in the leaf, which means it's really good tension. It's negative pressure. And so you get that developing in the leaf as soon as the stomata open up. You have the water molecules starting to evaporate into the air spaces in the leaf, and then they'll exit out the leaf, and then more water gets pulled up, and like clinging to the water molecules are clinging to the spongy mesophyll, and they start evaporating into water vapor. And you have that whole idea of the meniscus. You get smaller and smaller radii on this side as the water is clinging and receding. There's more evaporation into the bulk space in the air pockets there, and then out through the stomata. And so as long as that's continually happening, and as long as the water molecules are being cohesive with each other, sticking together all the way down, that whole water column is continuous all the way down to the roots. As long as that's maintained, you'll have water getting sucked up the plant due to the idea that the stomata opened up. So if you don't have the open stomata, you can't have transpiration. It's not going to work. Other questions on this idea of transpiration? We're still going to keep going. I still have a few more things to say, but anything about the mechanics involved on that? Okay, well, please make time to study, be able to work through that process. Okay. So, of course, plants live in a variety of different habitats. Here we're putting it together, kind of looking at the whole plant body now, where you're looking at the roots taking up the water and getting it primarily to the root hairs, and then getting that water to the xylem, more toward the center of the root. And then once it's in the tracheas and vessels, it will just be very easy then to course up the plant, be sucked up the plant as long as the stomata are open. So this is just trying to show kind of the path of the water through the plant body, and then they took measurements through the different areas of the plant body and looked at overall water potential values at those points. And they could show, measuring the soil and then moving up into the roots and then the leaves and then the outside air. So you're following less negative to more negative overall water potential ideas as well. Okay. So that's still happening. Now, how quickly transpiration occurs during the day, it really does depend on the habitat the plant is in. So, and now I'd like you to start thinking about yourself when you're out in the different habitats or different parameters. You know, it's different if you are, you know, hanging out in June or July or August. You might have days with really high humidity. You might have days with really low humidity. You might have a windy day, really still air day. So let's start thinking about these ideas now. And then just imagine yourself in these, under these situations, and think about, like, when do I sweat more? When does the sweat seem to leave my body more readily? Start thinking about that. And I think if you kind of get that in your head, we can talk about what the plant is experiencing as well. So, you know, we've had some very humid days recently, and humidity certainly can impact the rate of transpiration. How quickly will that water move through the plant body and finally exit the leaf as water vapor? And we can definitely see that the humidity is going to impact that. And so I often like to think about the concentration of water vapor inside the leaf versus outside the leaf to think about this idea. And so that's what this is representing: concentration of water vapor in the leaf minus the concentration of water vapor in the air. And if, if you think about a concentration gradient of that water vapor, that will help you, I think, figure out, is transpiration going to be fast or is it going to get slowed down? Now, when they've done measurements in the leaf of how concentrated is the water vapor, they find that inside the leaf, it's pretty much almost always saturated. So by default, plant physiologists say, let's just call it 100%. It's always really close to that. We're just going to say it's 100% water vapor concentration inside the leaf. So if you have 100% inside the leaf, but you know that relative humidity outdoors can vary tremendously from day to day, depending on where you're living. And so you have to start thinking about the gradient. So it's 100% inside the leaf relative humidity. What's the relative humidity, you know, on a June day versus an August day? It can vary. So you think about the gradient. So if it's 100% in the leaf, and let's say the weather person says it's 80% humidity, so 100 to 80, that's a modest gradient. But what if you're in, you know, September or something and the humidity drops to 30%? Well, 100 to 30 is a much steeper gradient, right? That's a bigger difference. And so the steeper the gradient or the bigger the difference in relative humidities, the faster, right? The faster the transpiration. It'd be like if you worked out and have a sweat building up, and then I stick you in a room that's 80% humidity, the sweat's not going to come off you very quickly, right? But then if I stick you in a room that's 30%, the sweat will leave your body pretty quickly. And so these are the ideas that we're thinking of. How much of a difference? Is it a big difference, a steep gradient, or shallow? All right, so think about those ideas as you think about the rate of transpiration. So the bigger the difference, the quicker the transpiration rates. And one of the things to think about, let me go back to this image. One of the things that's impacting water vapor movement out of the leaf is, I don't know, it's on both sides of the leaf, both the top and the bottom. But basically, this area right where the stomata are, right as the water vapor molecules exit the leaf, there's a so-called boundary layer. Every solid substance has a boundary layer. Your body has a boundary layer with the bulk air around you. It's just the layer of relatively still air molecules right at the surface of your body. Well, plants have that too. They have a boundary. And it comes into play when they open their stomata because it depends how thick, so to speak, that boundary layer is. How many layers of still air molecules are there? And if you can think about a windy day, for example. So let's say I make you, run on a treadmill, work up a sweat, and then I stick you in a room with no air movement. The sweat's not going to leave your body as quickly as if I stick you in a room that has a nice, massive fan blowing on you, right? So what's happening is that as the fan is blowing across your body or the leaf, that layer of still air molecules gets thinned out. They get disturbed and it gets very thin. And so it makes it that much easier now. Water vapor is a thinner boundary layer than a thicker boundary layer. You have to think about that too. Humidity tends to keep that boundary layer nice and still. Lower humidity, it's easier for that boundary layer to get disturbed. All right, so humidity also plays into that, but wind definitely really plays into it. Okay, so that boundary layer, how thick is it? And then anything that can thin out the boundary layer should speed up the exit of water vapor because there'll be less frictional forces under a thin boundary layer. There'll be less friction that the water vapor molecules have to deal with. Okay, so humidity certainly can make that boundary layer pretty still and fairly thick, relatively speaking. I tend to think in the terms of relative humidity, but you can calculate water potential of the bulk air too. You can do that, but for me, relative humidity differences are enough because I know inside the leaf it's roughly 100%, and then I just look at the difference of what is it in the bulk air. So here you're looking at relative humidity in different parts of the leaf and bulk air. And then just trying to show you that if you calculate the water potential, you're still following the idea that the water vapor is going from less negative to more negative as it moves from inside the leaf to outside to the bulk air. So you still have that flow of less negative to more negative, which you can see in the final column there. Okay, so we just, so thinking about temperature too, again, think about you running on a treadmill, and then I stick you in a room that's 90 degrees, or then I stick you in a room that's at 50 degrees. All right, so think about how easily does the sweat come off your body. And so again, the steeper the gradient, so to speak. So inside, oh, and then this idea. As the temperature rises, the water holding capacity of air increases. So here's a graph to prove that. If you're think about sometimes seeing the visual is helpful. So here you're looking at air temperature in Celsius on the x-axis, and then the water vapor concentration on the y. With increasing temperature, the holding capacity of air increases as well. So, and then they range it from, 0 degrees Celsius all the way up to 45. So your body's about 37 degrees Celsius for reference. So you can see on a nice hot day, you have better water holding capacity. But again, temperature, oh, and then too, think about the idea, let's say I make you run on a treadmill and I make you wear a black sweatshirt. And then I put you on a treadmill and you work up a sweat, and then I put you in a room at 90 degrees and it's sunny. I have a sun heat lamp on you. And then if I put you also in a room where it's cooler, I mean, I think you know just by living your life, if you wear a black t-shirt or black sweatshirt and it's sunny out, you're going to get warm, right? So think about that too, because leaves are not colorless, they're green. So they're absorbing heat energy. If you measure the temperature of a leaf, it is hotter, it's warmer than the bulk air around it, for sure. Just like if you wore a black sweatshirt in the sun. So think about those ideas too. So if the leaf is heating up, it will also increase the transpiration rates. All right, so increasing in heat, and then you have to factor in that the leaf temperature is going to be hotter than just the bulk air because of the pigmentation absorbing that heat energy. And so you have the energy of the water vapor molecules inside the leaf. It's very revved up. Okay, the molecules are bouncing all over. Transpiration rates are going to be quicker. So the wind, the fancy way to say that, I said it decreases the boundary layer. And they often will phrase it as it modifies the length of the diffusion path of the water molecules, the vapor molecules. So it's just saying that you thinned out the boundary layer. You make it thinner, that means the transpiration rates can go faster. Okay? So the boundary layer, like I said, any solid substance has a boundary layer with the bulk air around it. And so leaves, I'm sure you appreciate, many, many different leaf morphologies out there in terms of like the surface area, the thickness, the shape, whether or not you're going to have leaf hairs. What's the fancy word for leaf hair? Trichomes. Okay. So the trichomes, of course, some leaves are super hairy, have lots of trichomes, and then trichome design varies tremendously too. Just the shape and whether or not it has a gland on it. And so there's a lot of difference there. And then where a plant will design its placement of its stomata will vary depending on its habitat. And so they can vary all of this in response to the habitat that they're in. And even the same plant, it's not like it has to, it certainly gets passed on to the next generation as that plant continues to live in that habitat. But even plants that have been experimentally studied, where they shift the habitat on that plant, they change the environmental parameters, and they can show that that plant will start making, like the new leaves that it starts making as it's getting exposed to that hotter condition, for example, it'll start making more trichomes. So you can actually manipulate the number of trichomes on a plant by some environmental pressures that you put on it. And in this case, it's usually heat or drought, or both. And so their plants are amazingly plastic in that way, where they can start to modify their own body. It isn't just until the next generation comes up that you'll see a change. They can do it in their own lifetime. So I won't, ask you to calculate this, but sometimes it's helpful as you're studying just to think about an equation and play with it a little bit to convince yourself that the time of transpiration rate, essentially how fast does it happen, certainly does depend on the distance, and then the K and the those two, the diffusion coefficient. Those are values that are given. I'm not going to ask you to calculate that, but just thinking about ways to decrease the distance, essentially. Okay. So decreasing the boundary layer is the big thing. If you can thin out the boundary layer, you'll get faster transpiration rates. So I've shown this before in Plant Kingdom class, but if you haven't had that, you might be skeptical to learn that this is a leaf. This is a cross section of a leaf. It doesn't look like the average leaf that's ever shown to you in most textbooks, but this is a plant that has a really nice strategy of altering where it has put its stomata. And so here's the top of the leaf, and there's no stomata there. I don't see any example of guard cells and pores. Here, where my laser is doing the bottom there, that bottom, there's no stomata there either. So then you're like, okay, well, the leaf has to have pores, so where are they? So then you start following the perimeter here up, and then you're like, oh, let me blow this up. Now it's blown up. So if you start working your way here, guard cells. So they've tucked the guard cell, the stomata, up into this recessed tissue of the leaf. Anyone remember what this is called? Sunken stomata. The way that this is so drastically recessed, they gave it special term, special kinds of sunken stomata. They actually use the word stomatal crypts. And so that's a strategy. Think about it for a second here. You hide away your stomata, and this is the outside relief. Look at that. You've essentially created a huge boundary. The distance from the stomata, all of this air is going to be really still air because it's really hard for wind to go right up into the bottom of the leaf. So this is still air, still air, still air, still air, still air, and even this type of layer. That's a huge boundary. What's that going to do to your transpiration rate? It's going to tank it. You're going to go slow. So if you're a plant and you design this, where do you think, what kind of general habitat might you be? Yeah, in the desert maybe, or certainly consistently dry, droughty, hot, where you want to conserve water. You don't want water flowing through you really quickly, okay? So this is an awesome strategy for those types of plants because they've effectively just created a huge boundary layer, still air. And so that's really going to slow down transpiration. So really brilliant. Here is some measurement data to get you thinking about this idea of still air versus moving air and looking at the stomatal aperture on the x-axis and then the rate of transpiration. Anything you see flux, that just means movement of something. In this case, it's water. So here, what you're seeing, if your aperture, well, you can see that the boundary layer, you have nice still air, you have a pretty thick boundary layer. And so if you have your stomata more wide open, you do get a little bit more transpiration, but you can see it's not super dramatic. But when you put a fan or something on that, you know, a nice wind, and then if you have wide open stomata, you're going to get really good transpiration rate. So I'm just getting you to think about the difference of still air versus moving air, messing with the boundary layer. Okay, so certainly their habitats can greatly impact their transpiration rates, for sure. So we've talked about the mechanism, we've talked about ways that it can be shifted by its environment, but why even do it in the first place? The vast majority of water that a plant takes up goes out its stomata, the vast majority. And so it must have a reason. There must be a reason for them to draw up so much water. but then also have it exit the leaves. So, whoops. So if you're a plant, why would you bring up water into your body? There's several good reasons. Structural support, right? Because that gives you some really good turgor pressure. So that's a great idea. So you have to remember now, as the water is moving through the xylem, some of it gets siphoned off into the rest of the plant body, right? I mean, it's not like it just totally stays in the xylem, because you have to make sure that the cells are hydrated, right? So you have to think about that. Certainly water's getting taken up to just nourish the plant body in terms of every living thing needs hydration. And then the turgor pressure is great because now that a lot of it's going into the vacuole, which is pressing against the cell membrane and cell wall. They don't have bones, so they need a way to have some rigidity. All the goodies. That's an awesome reason, right? So I've said there's, soil water is not pure. I've been saying the plant takes up the water and the dissolved minerals. Takes up the water and the dissolved minerals. I'm saying that a lot. And so the dissolved minerals are a huge payoff for the plant because they can't pop a vitamin like we do. All right, they have to get their minerals from the soil. That's why soil health is so incredibly important. Right? Plants can't make their own minerals. They can make their own sugars, which is awesome, but they can't make their own minerals. All right, so certainly getting their mineral nutrition is huge. Could there be any other reason why they might want to exit water out of themselves? Yep. So the idea is kind of a indirect benefit, I guess, in the sense that as soon as water vapor is exiting the leaf, well, that means that CO2 can come in because that means the stomata are open. So once the stomata open, yes, you have transpiration, but then another big payoff is you can take in CO2. It's like, they can't just open the stomata and say, oh, water, don't leave. Please don't leave me. That's not going to happen. So water is just going to automatically exit the plant, but the payoff is CO2 is coming in for photosynthesis. So that's another huge payoff. Having stomata open, certainly you have transpiration kick in, but sometimes, there are volatiles that plants give off through their stomata. So that could be another benefit of having open stomata. And, it is causing transpiration, but it could also allow for volatiles to be given off. And so we'll talk a little bit more about volatiles later in the semester. So of course, this is a huge deal. If you grow plants for a living and need to have enough money to live off of that, you want to make sure that you irrigate your plants, but not over or under irrigate your plants. So of course, they've looked pretty heavily at this idea of what is controlling the stomata. How does the plant decide to open the stomata? And the better understanding they can have of that, of course, the more they can fine tune the growing of the plants. Okay, so this is going to seem weird, but when you have those two guard cells that are surrounding the pore, to actually get the guard cells to reveal the pore, they have to fill up with water. And when I was first learning this, I thought that doesn't make sense. It's just the opposite of what I would think. But that's what they see happening. When they experimentally measured this and they were trying to figure this all out, they're like, oh, look at that. When the stomata are open, the guard cells are full of water, good turgor pressure. And so what happens is there needs to be a way for water to get into the guard cells. And the way to do that is to follow the law of water potential. And so you have to create a situation where the water potential, to get water to flow into the guard cell, what's the water potential in the guard cell compared to, water, yeah, more negative. So the guard cells have to create a situation where their water potential is very negative compared to surrounding cells. And if they create that situation, then water will move into the guard cell from less negative water potential to more negative water potential. Well, the way to play with that, if you're a plant and you're trying to create some cells that have really good negative water potential, the easiest way to do that is mess with your solute, your cytosol. So if you can get your guard cells to get either synthesize more solutes or get some import of solutes, so you get lots more solutes in the guard cell compared to surrounding areas, then you'll get a nice negative water potential. So the osmotic uptake of water, what that means is the plant has created a situation where there's more solutes in the guard cell, and water will flow in result because of the laws of water potential. Well, then as soon as that happens, of course, as soon as the water is flowing into the guard cells, that puts pressure on the cell membrane and cell wall, so you get that hydrostatic pressure, so your P value is also going to increase. You can't ignore that. So they experimentally could measure all of this under controlled conditions in the lab. And then they started thinking about real life, like, okay, how does a plant do this in real life? So of course, they suspected, well, okay, so the sun comes up in the morning, it hits the plant starts doing photosynthesis, and sugar gets made. So it's probably sugar going into the guard cells. That would be a good solute. And it's being made, right, in the morning, so it's probably sugar. But when they went and investigated guard cells, they found it wasn't sugar, at least not in the morning. Instead, it was potassium. So that was a bit of a head scratcher. So they would experimentally measure that potassium was actually flowing into the cells. It was getting imported into the guard cells. And that was causing the solute concentration to increase, which drives your size of S very negative, and then water will rush in. So when they did this through the day, though, so they say, okay, first thing in the morning when the plant opens up its stomata, it's actually potassium that's built up to high levels. And then they kept measuring through the day, and they saw, oh, now it's shifting. Now it is sucrose. So later in the day, during a good chunk of the daytime, sucrose does take over as the solute. So what they discovered is that when sunlight strikes the plant, and we'll talk a little bit more about this later in the semester, but when sunlight strikes the plant, the blue quality light of the sunlight will trigger the mechanism that allows for potassium to get loaded in to the guard cells. So it's a very fine-tuned process. The plant is actually sensing blue light, and that will trigger potassium import, and that will get the uptake of water. And what happens is, if my hands are the guard cells, and if I'm in the kind of the prayer position like this, that means the stomata, the pore is closed. But as water rushes into the guard cells, it actually creates a force that will cause the guard cells to move away from each other. And that's what reveals the pore, okay? So water rushes in, they actually move away from each other, and then you have the pore. Water rushes out, and you have the opposite. That's what causes them to close over, all right? And so here on this graph, you're seeing the import of potassium early in the day with open stomata. And here you can see the blue potassium level. And then you can also see sucrose starting to build early, but then it really takes over during the rest of the day, essentially. All right, so, and then the black line here is stomata aperture, that just means how wide open is the pore. So certainly this nuanced idea of it's not sucrose to start with, it's actually potassium in response to sunlight. But another thing that really does matter for the plant is CO2, but not bulk air CO2, because that's pretty constant. I mean, it's like 0.04 something. No, that is staying pretty constant. So that's not what I'm talking about. I'm talking about the intracellular concentration of CO2 inside the leaf. All right, so concentration. So intracellular concentration. So the plant is constantly needing to assess how much CO2 do I have in my leaves? How much CO2 do I have in my leaves? Oh, I don't have enough. I'm going to open my stomata. But there might come a time when it's like, okay, I've taken in quite a bit of CO2, and then they can close down their stomata quite a bit, or maybe all the way for a little bit. And then when they sense levels dropping in the leaf, they'll open up, take more in. So it's dynamic. They can do that, and especially if they're trying to conserve water. They will keep constantly assessing how much CO2 do I have in my leaf, in my leaf, in my leaf. And then they will open or close in response to that. They also have done lots of experiments with light. You shine a light on a plant, sunlight wavelengths, and that will get the stomata to open, of course, because they think it's time to do photosynthesis with the light. Darkness, they won't do it. Of course, water status plays into the stomata, opening or closing, right? If they're well hydrated, they can risk opening their pores wide to get as much CO2 as they can during the day. But if they're under dehydration, they're going to have to be a little bit more careful. So certainly water status of the plant and temperature. So, warmer temperatures to a point, the stomata can stay open. Temperature kind of goes in line with water status. If you have high temps through the summer, not a lot of rain, they're going to be pretty careful about how far open and how long they have their stomata open. So, but CO2 is actually a pretty big one because that's what they use for photosynthesis. So they need to always measure and respond to that. So here are the guard cells, and you can see the pore in between. And so when they were first doing this research, they noted that many guard cells have lots of chloroplasts in them. And so that's why they thought it was sugar that was allowing for the osmotic uptake of water. But then they discovered many plants that don't have chloroplasts in their guard cells. That kind of put a wrench in the hypothesis, and they started investigating a little bit more carefully. So anyways, on the left is open, on the right you see it being closed. Here you can see the stomatal aperture. And so with this experiment, what they did was just hit the plant with just red light, just that quality. And you can see that the stomata is kind of opening. Yeah, it's somewhat there. But then right at this point of the experiment, 2 hours in, they exposed the plant to full-on blue light. Then you can see how much better they were able to open up their stomata. So this is why they're thinking that the blue light is really necessary to kick in a lot of potassium import into the guard cells. Okay, so here again, just going back to the whole plant body and thinking about this water being brought into the roots and then getting into the vascular tissue, into the xylem, where it can be brought all the way up to the leaf. As long as the stomata are open, that can happen. So water is literally sucked up the leaf due to the nice tension that's developing in the tissue. And as long as all the water molecules are cohesive with each other, you have that bulk water movement all the way up to the leaf. Okay, so that's it on transpiration. You can draw a line. This is it for the exam content. Okay. I don't like to give you exam questions on stuff we covered. So, the exam's Friday. I don't like having you memorize stuff or learn stuff from Wednesday's lecture because that's not enough time. So we're stopping here, and then what we get into next will not be on this first exam. Okay, let me just introduce the topic. Is it in EduCAD on film translocation? Okay, I'll post it. I'm just going to introduce it. So there's going to be just a few slides here. So the next topic we're getting into is phloem translocation. So we're still sticking with the vascular tissue. Okay, so we're still focusing on that, but now we're looking at the tissue right next door, so to speak, to the xylem. We're looking at the phloem now. And so xylem and phloem is clustered together, but they have very different roles to play in the plant. And so we said the water movement's unidirectional, starts in the roots and goes up to the leaves, and that's it. All right. Phloem, that's not the case. When they did all the measurements of what's happening in the phloem, they could see there's, and it's not in, there's clusters of phloem tissue. So some of the phloem is directing movement toward the leaf, another nearby phloem is directing it down to the roots. And so you have movement in every which way when it comes to phloem. So the laws of, the tension gradient and all of that we just discussed can't really hold the same way with the phloem. So they had to kind of go back to the drawing board and say, okay, how does this all work with, we're taking these measurements and seeing that movement through the phloem can be in any direction. And so what kinds of laws and principles would account for that? So we're primarily focusing on sugar movement through the phloem. There's other things that move through the phloem, but dissolved sugar. So water with dissolved sugar in it is moving through the phloem. And then there's other stuff too. We'll get into that. And so you have to think about parts of the plant that need extra sugar. Either they can't do enough photosynthesis themselves to meet their own needs, or they don't do photosynthesis at all. So potato tubers, for example, they can't do their own photosynthesis because they're buried in the soil. So they have to demand sugar or request nicely sugar from the leaves. All right, and they will communicate to the leaves, please give me more. I need to build my lovely tissue. Okay, same with other fruits. Believe it or not, that's a fruit. I know everyone wants to tell you that's a vegetable, especially now the fall season, all the gourds and squashes and everything is getting more common in the store. It's a fruit. You're gonna freak out your friends when you tell them that, but it's the truth. Okay, it came from a flower, right? That was once a flower. So by definition, that's a fruit. The potato tuber, not the other squashes and gourds. All right, so those will need extra sugar as they're building because the sugar content, starch content is high in these types of these parts of the plant. So we're going to zoom into the phloem. So I'm just putting this here to remind you that the vascular tissue is clustered, xylem and phloem together. Here they're showing the nice big thick cell walls on the primary xylem. Phloem tissue is much more delicate looking under the microscope. It doesn't have that thick secondary cell wall. So if it doesn't have a secondary cell wall, is it alive or dead? It's alive. It's highly modified because they've lost a lot of their organelles, probably because they get in the way of the movement. And so, so they call them alive but highly modified cells. All right, so the primary phloem. And they look much more delicate because they don't have that thick secondary cell wall. All right, and then again here you're looking at a stem, and see this is what we would refer to as wood of the tree trunk, and then the phloem again it's got more delicate looking. Often it's stained the blue green. Look at it under the microscope. It's my eye. It looks kind of blue green. Okay, so you can see that they're in a tree trunk with a lot more xylem than there is phloem. And then here's another representation of I call this the Mr. Bill morphology. Probably don't have no idea what I'm talking about. It's way before your time. But the eyes, the nose, and the mouth, that's xylem, that's the vessels. And then the cheeks are trachea. And then the forehead is where you find the phloem and the associated companion cells. Okay, so we tend to talk about the sieve tube elements and the companion cells. We tend to talk about them as a complex because it's a one-to-one relationship, and it's the companion cells that's metabolically helping out the modified phloem. All right, so we'll stop there and continue on. Okay. Yeah, that's Mr. Bill. There used to be a cartoon like with a clay animation, and he would always get smucked, flattened in some escapade, and so he'd do that face. Oh no! Huh? Yes, they did from Friday, right? Yes. So yes. So I'm gonna forward. I have a meeting with them today, so I'll let them know and I'll forward your email. But that's awesome that you can earn money out like that. But like I did but so what I did was that's really yeah. That's good. You're using your knowledge. That's awesome. Yeah. I know. What works for you?
Yeah, I can email you. I saw tomorrow. You have them. That's
So let me. Oops. Hang on just a second. My computer is freaking out. Okay.